Morning, everybody. Welcome back. As far as I know, there's nothing I need to warn you. Oh, there is one thing I have to warn you about. Graphs tomorrow. You see, I posted an announcement. The room has changed. There'll be signs up. You'll know you're in the wrong place when you walk into the room and there's nothing but teenage girls in the room. Okay? Our Women in Engineering Day is happening tomorrow. We're inviting high school students from all over the place to come and celebrate engineering, do projects with us. And I am going to be teaching the morning sessions of that. So I'm one of many people. But I'm around, and the tutors will know how to find me if you need me. Like if we need to solve a Wiley Plus issue, round off, like, you know, those kinds of things that only I can get into. They'll know how to come find me, and I can probably sneak out. So don't hesitate to like come to GRASP and ask for Mr. Balogh. They'll come get me. GRASP is in, 337? Yeah, it's up chemistry floor, okay? Third floor. And there'll be signs, right? If you come to GRASP tomorrow, and there'll be signs on the door saying GRASP students go to this room. So we'll guide you around, but that's where I'll be tomorrow. Next Friday, again, I plan on being around, but there's a ribbon cutting ceremony for the building. And I think I'm going to be a tour guide that day for part of the day, like starting around 10 or so. I apologize, like come to GRASP, again, they'll know where to find me, and I'll welcome your guys' interruptions because you'll save me from having to tour the mayor or somebody around the building. But if you need to get a hold of me, if you want to have one-on-one time, whatever, email me and I will make time for you, right, during the week. Normally I don't have time, but I'll push everything aside for you guys because I know that the next 2 Fridays in GRASP, I'm going to be sort of in and out and all over the place. All right, let's see. We were doing friction, right? How many different kinds of friction are there? 2. They are static and, how do you tell the difference? Kinetic means that where the 2 surfaces come together, where the friction's happening, those 2 surfaces are moving relative to each other, right? It's not just motion alone. If somebody is riding a skateboard, okay, across the ground, what kind of friction exists between their feet and the board? Static. Even though they're moving? Yes, because the skateboard and their feet are not moving relative to each other, right? They're not slipping or sliding relative to each other. But what kind of friction exists between the wheels and the ground? Ah, good, I tried to trick you. It's static. And it's, even though the wheels are going around, the contact surface, right, that patch where the wheel comes in contact with the ground, again, not slipping or sliding. So keeping those things straight can be a little bit difficult. Last time we wrapped up with this, okay, where we added friction to our sliding cow problem, right? And now we're going to do the same problem that we did back in chapter 5 with the connected objects, the mass 1 and mass 2. Only this time, we're going to throw friction into the mix, okay? So let's get that set up, and we'll try to have relatively the same picture that we had last time. Let's get our physics hill all worked. Oh, that triangle came up weird. That's all right. All right, so we'll have mass number 1 sitting right there. We'll have mass number 2 right there. Let's do all the things that we had last time, right? This is kind of second time through, as it were, right? So I'll go a little bit quick here, right? So we got the string, we got the pulley. Let's see, we had tension going up that way. We had a normal force. And then we had gravity. There shouldn't be any like huge revelations about any of those forces. Again, we've been here before. You can flip back into the notes from chapter 5 and see what's going on there. Okay, mass 2. We've got the earth pulling down on it, and we have the string pulling up on it. So far, so good. Again, no friction in this problem yet. But in order for me to add friction to this problem, we've got to know some things, right? We need to know whether or not this object is sliding, like mass number 1. Is it sliding up the hill? Because if it's sliding up the hill, what kind of friction is it? It's kinetic. And if it's sliding up the hill, then we know the direction that the kinetic friction is acting. Which way would the kinetic friction act? Down, because kinetic friction always opposes the direction of motion. But what if mass number 1 were winning, right? And it was sliding down the hill. Then what direction would kinetic friction point? It would point up the hill. But what if mass number 1 isn't sliding at all? What if it's just stuck there? It would be static. But what direction would static friction point? Your choices are up or down the slope. Are we good there? It's going to be in the plane as perpendicular to the normal force, because the frictions are always perpendicular to normal force. Okay. So the question is up or down? What's the answer? Both. Yes. The answer is it depends. What do you mean it depends? Okay. Here's the problem with static friction. You don't know until you dive in and do it both ways, really, is what it comes down to. And like I said, there'll be penguins to torture you on the homework. Let's say that the static friction is acting up, right? Okay. What's acting down? Like, what's the force that's pulling mass number 1 down? Or at least trying to. Gravity. Okay, so let's get in here. These components of gravity are going to be the same. We've been here before. M1g cosine theta, M1g sine theta, right? That doesn't have anything to do with friction. So right now, do we have the ability to get 0 force in the x direction for mass number 1? Are there enough forces acting in opposite directions to possibly have this add up to 0? Yes, right? We have the component of gravity that's acting down the hill. So there's our negative. I know I haven't said anything about acceleration or directions yet. I'm just doing concept. Here's my force pulling down the hill. Here's my force pulling up the hill. Is it conceivable or possible that those could be equal in opposite directions? Sure, right? Again, the answer is it depends. So technically, we don't need friction, right, in order for this to be just sitting there. So one answer for static friction could be 0, right? None is necessary. But why would friction, static friction, act down the hill? What has to be true if static friction was starting to act down the hill? The tension is too big. The tension is bigger than the gravity pulling it down the hill. And so to keep the surfaces in contact and not moving relative to each other, static friction will point down the hill. So what would cause static friction to point up the hill? If the weight, if the component of gravity pointing down the hill were bigger than the tension. If your brain is already mush, welcome to static friction. Static friction will be whatever direction and whatever magnitude it needs to be in order for the surfaces to do what? Not move relative to each other. And static friction strength depends not only on the normal force. Remember fun, right? Because friction and normal forces are related to each other through the coefficient. So not only does it depend on the normal force that's there, but it depends on all the other forces that are there too. Which means when static friction is involved, you generally have to test all the cases, right? And what I do is I start with like, okay, how much do I have pulling this way? How much do I have pulling that way? Who's winning, right? And then I'll kind of figure out where static friction is in the mix. Static friction will keep the acceleration of this mass to what? How is the motion of mass 1 changing if static friction is involved? It's not. It's 0, isn't it? Which means you must have 0 net force. All the forces in the x direction, all the forces in the y direction have to add up to 0. That's your secret weapon when it comes to figuring out static friction. In homework, especially the penguin problem, the problems are going to say what's the maximum static force and minimum static force or something like that, right? What they're asking you to do is not contemplate all the possibilities, but just look for the possibilities where like the object's just barely starting maybe to slide down the slope, or maybe just barely getting to be pulled up the slope. At that point, you know that whatever forces are acting, right, static friction is equal to the opposite of them. So play around with it. Think about what it's going to mean for objects to stay in one place, right, and the directions that other things pushing or pulling on that object are doing so, and then work out what static friction needs to be so that you have 0 net force. That's sort of like the key with static friction. Because the surfaces are not moving relative to each other, right, we know that the change in motion, the acceleration, is going to be 0. Having said all that, let's do kinetic friction. Let's do the example using kinetic friction. So I am going to say that mass number 1 is losing. In other words, mass number 2 is big enough for this thing to be sliding up the slope. Okay? It could be not accelerating up the slope. It could be just sliding, where it's not speeding up or slowing down. But for the sake of this example and being in the biggest general case, I'm going to say that it's sliding up the slope, and I'm going to guess that it's speeding up as it slides up the slope. Could be slowing down. If I'm wrong, I'll get a negative acceleration. But I'm going to say, all right, we know the velocity is up the slope, right? We know it's moving. We know it's sliding up the slope. Gives us a key that it's going to be kinetic friction. And then I'm going to guess that the acceleration is also the same way. Again, if I'm wrong, I'll get a negative answer. Yeah?
So we're assuming what the velocity is?
No, I'm telling you that it's sliding up the slope.
Oh, okay.
Yeah. That's something along with the angle and the masses and the coefficient of friction. Those are all things that I'd have to know to be able to solve for an acceleration. Okay. All right, so let's put in our friction. So if the box is sliding up the slope and it's kinetic, which way is the kinetic friction pointed? Down the hill. There it is. Okay, so now I come over here, again, mass number 1, mass number 2. I have x and y directions for both of these things. And I didn't specify coordinate system. Up the hill is positive, away from the hill is positive. And then to make sure that I'm consistent, if I said up the hill is positive, what direction do I say is positive for mass number 2? Down. Got to stay consistent, otherwise my vector signs are not going to be happy in my equations. Okay, this means that I can write down m1a equals, for the x direction for mass number 1, and in the y direction I can just write down 0. Why am I allowed to write down 0 for the y direction for mass number 1? I made sure that the only acceleration was in x, and there was none in y, which means m times a, and a being 0 in the y direction, okay? And then over here for mass number 2, there's no acceleration in the x direction. So I can just write 0 equals there and get on with my life. m2a equals, so there's kind of like my template, right? This table, this thing that I'm making over here with mass 1 and mass 2, that is really something that's been the same the whole time, hasn't it? I haven't really varied that. Our free body diagrams change depending on the situation, right? But then I have something that looks like this. All right. You tell me, what do I do next? Help me, Mr. Balogh, I'm lost. I don't know what to do next. What would you say? Find your forces, right? Okay. So I'm still confused, and you need to help me. You need to give me a little bit more. Sad puppy dog. Well, okay, I already did. Right? I found my m1g cosine theta, my m1g sine theta. I've got my template. What do I do next? This is where you look at me and tell me to become an English major? No? Tell me it's going to be okay? It might be in my best interest, right? Yeah. I've got MA equals. What do I have to put on the other side of that equal sign? I got to put forces, right? What forces? You would tell me, okay, look along this line that you've defined and add up all those forces, right? Make a list of all the forces in that horizontal direction. What are those? Tension, m1g sine theta, and friction. And then you'd remind me that at this point I have to do what? Go back and put all the signs in, right? Good. This is great. I'm getting you guys to teach the class. I don't need to be here anymore. Plus t, why plus t? Up the hill. m1g sine theta, down the hill. And friction, down the hill. I'm not going to guess. I know that you need practice with doing that, okay? Beyond like being here, right, with me, within the Mr. Balogh bubble, which is a real thing because students complain about it all the time. Mr. Balogh, I understand in class, and then I leave and I don't understand anymore. How do you get practice? Homework. Rewriting your notes is rehashing stuff. But if it works for you, it works for you. It's not a bad method, but we want new additional methods, right? Where can you go get a lot of practice problems? Don't say the internet. Oh, still say the internet. I have a hack for you. This is a shortcut. It's a hack for success in this class, right? Read the book. Right? Because at the end of the chapter, every chapter, there's what? 100 or more practice problems, right? Of which I've pulled 10 for the homework, okay? Leaving 90 more for you to, right? And I'm not saying that you need to go and do 100 problems a week. No, that's insane. But those problems have situations in them, right? And you can either look at the picture that's provided or read the words and just practice drawing the diagram for it. You don't have to solve the whole problem, right? Just practice drawing the diagram and trying to figure out the forces. How many mistakes are you going to make on those? A lot, right? That's okay, right? Because you'll be like, I have no idea if I'm doing this right. And then you'll email me or you'll go to the tutorial center. You come to, you'll just like, hey, am I doing this right? And we'll be like, no. Or, yeah, right? Like, and then you learn. Right? You learn by seeing more and more of those things. So don't be afraid to just take a few of those, try them, see what happens. Don't get discouraged if you can't do it. It's fine, right? But your brain needs to be chunking away at this stuff before it can get to a point where it's confident in writing this stuff down. All right, y direction. Kind of looking along this line, right? I don't think, nothing changed here, did it? From last time. If we go back and look at that other one, we'd see that this y equation right here is exactly the same as we had for the other connected objects without friction. The only addition to our entire set of equations is going to be that frictional force right there. Okay, in the x direction for mass number 2, it's boring, but true. All right, and then in the y direction right here, I'm going to have m2g minus t. Did I get that right? Don't just say, yeah, Mr. Bailey, you're the teacher. You always get it right. No. Check and see. Should m2g be positive? Yeah, we define down as positive. Why do we define down as positive? Because that's the direction of the acceleration, even though I didn't draw it, right? Consistent with the direction of acceleration for mass number 1. I mean, I know mass number 1's up the slope, and mass number 2 is down, and those are different directions, but they're connected by string, right? So I'd expect them to be moving together for that tension to work the way we say it's supposed to work. All right, now what? Visualize and strategize is mostly done. A little bit more strategy to go. What are we looking for probably? Like kind of what's the point of Newton's second law? What are we solving for? Acceleration, okay? So we've done that. We've got equations. So we're going for acceleration. Knowing where we need to get to is one part of the battle, right? So we need to solve 3 equations for, golly, how many unknowns are there? 1, 2, 3, 4, and then that's a repeat and that's a repeat, isn't it? Okay. 4 equations. 4 unknowns, 3 equations. What do I do? Where's the 4th equation? Fun. Got to remember how much fun friction can be. No? No? All right. The puns the dad jokes are an added layer of cruelty in this class that I bring. Right? It's not a part of physics. It's just me. Okay. So 1, 2, 3, 4 boxed blue equations, and we're solving for A. But we could also solve for T. For those of you that are having a disturbing sense of déjà vu right now, you've actually done this problem. Where did you do this problem? Lab 1. Problem number, what was it, 4 or 5? I can't remember. Right? The last one? Okay. The big algebra jungle, oh my gosh, Mr. Balogh, I can't believe you made me do 3 or 4 equations with 4 unknowns. Bread and butter. Remember I told you back then how the 4 equations, 4 unknowns would be the easy part? Like we can finally get to the math and just do some algebra? Look at all the stuff that we've had to do to get here, right? But the physics is very much, right, all the stuff that leads up to the point we're at now where we got to do the math. And I'm not going to do the math here, right? See lab 1, right, okay? Because you solved this math problem. We gave you numbers because I guess we were feeling nice that day or something, right, okay? I'll give you the symbolic solution here in a second. But let's get really real for just a second, right? How many of these types of problems could I put on an exam where you have 10 minutes per problem to do? 0 is the correct answer, isn't it? Like, I could drop one of these on an exam and you guys would be like, I can't finish in 70 minutes. Right? So there's 2 things that need to happen here. You need to get proficient, right? You need to get fast without making too many mistakes along the way. Or we need to focus on what's important, And you know me well enough to know now that I don't think the math is all that important. The math is a matter of using skills you've already developed and passed in other classes. The math is not so much critical thinking as it is sort of pattern matching and doing algorithms to get out what we want, right? There's skill in it. This is a physics class, so what do you think I'm going to focus on? The physics, right? So I have, and quite possibly will, I haven't written the exam yet, but I could give you questions on the exam where I'm saying, just set up the problem, right? Just give me the equations, right? Don't worry about finishing it, right? That's one way to kind of shortcut a problem, right? And still focus on the physics. I could give you a problem where here's a free body diagram, here's some equations, identify the mistake, right? So these are ways that I can ask questions where it's conceivable that you could get some traction in it in 10 minutes, right? And you could still show me that you developed the critical thinking skills and knowledge necessary, right, to be successful at Newton's second law. I've also been known to give problems where you set it up and then the algebra is like one unknown, right? I've kind of just given you just enough so that the algebra is dead simple to do, right? And takes all of like 30 seconds to 1 minute. Just, okay, I got the numbers out, I'm done, right? So again, I will engineer the exam to be such that the expectation would be for a total noob that's worked at it for a couple of weeks to be able to do a problem in 10 minutes. Maybe 15, but if I've got a problem on there that's going to take you 15 minutes, I'll also give you another problem that will only take 5, right? So there's a little bit of wiggle room I have there as well, right? And again, every problem on my exams is worth exactly the same number of points. So if you're staring at a problem with 2 connected objects and you're expected to find something, what are you going to do with that problem? Save it to the end, right? Because it's a difficult problem. You know it's going to take a while, so you might as well get everything else out of the way before you start sinking some time into that one. Better to lose that one really difficult problem rather than lose 3 or 4 really, easier ones for you to do. So realize all of that, right? Okay, that I'm going to make it so that I feel like you can do a problem in 10 minutes, even though on your homework you will spend 1 to 6 hours on a problem, right? Just trying to figure it out. So we'll try to meet in the middle somewhere there. The feedback I got from the first exam is that it was easier than the homework, right? Okay, and that again, by design. And don't let off the gas. Don't just sit there and go, oh, well, homework's so much harder, I'm just not going to pay attention to it. That's death, right? Over-prepare, really nail this stuff, and then hopefully the exam will be straightforward. For some of you, grades are going to suffer on this next exam. It just is going to happen because it always happens. It just always happens, right? Just work hard, and you'll be all right. Answer. The acceleration is m2g, so the symbolic version, m1g mu cosine theta plus sine theta all over m1 plus m2. That's what I got for the symbolic answer for the acceleration. You then just plug that back up to find the tension, and away you go. At some point, you kind of give up on checking these things, right? It's like, right? How do you check this thing? There's really no way around it. You run simulation, you do experiments. You get somebody else to do the problem and check and see what they got. And if you're in agreement, you're either both wrong or both right. And that's what we call science. Okay. I'm a little bit ahead of my timeline. So let's talk about a couple more things here. I'm going to just throw this on here, and we're going to cross off that. Let's answer a different question. Let's put our cow back on the hill. Do you guys want a different object now, or are you good with cows? Ford Bronco this time? I'll do my best to draw a Ford Bronco. There you go. Okay. It's got mass. Let's, we're going to put this Ford Bronco on a hill, parking brake on, and Ford Bronco will not be sliding down the hill. Okay, that's the situation. Find the coefficient of friction necessary for this Ford Bronco, this car, this truck, Jeep type thing, to not slide down the hill. We're not talking about rolling. Rolling's in chapter 10 and 11. Okay, we're just saying with the parking brake on, right, the car's not going to be slipping down the hill. So our goal this time, notice, I'm asking about coefficient of friction, right? I'm not asking about acceleration, because if this car is parked and not slipping down the hill, what's its acceleration? Zero, right? So we already know that the acceleration is 0. We know the angle, we know the mass, we know what planet we're on, okay? Our question, the thing we want to find, is what is the coefficient of friction? Now, this brings up a wee bit of an issue. Let's see if we run into that issue as we go. Name an object pushing or pulling on the car. The Earth, all right. Gravity, mg, got the weight, okay. The hill, which now consists of 2 forces, right? Not just a normal force, but we know friction is present. We know what kind of friction it is. So now it's striking fear into our hearts and minds, right? Okay, because static is weird. Okay, all right. So what direction is the static friction pointed? Up. How did you do that? Gravity has a component down the hill and into the hill, right? So this is m1g cosine theta like it's always been. This is m1g sine theta like it's always been, right? We have a balance of forces on the line that goes in or out of the hill, right? Along our y-axis, which I haven't specified yet. So normal force and m1g cosine theta are balanced. What's the unbalanced force here? m1g sine theta, the gravity pointing down the slope, right? Well, you can't have an unbalanced force in the x direction and have 0 acceleration. It's impossible, right? ma equals sum of forces. If a is 0, and the mass isn't 0, which it isn't, okay, then the sum of forces has to be 0, which means we're missing something. We know the thing that we're missing. We know it's friction. And so which way is static friction pointing? Up the hill. It has to be, in order for this acceleration to be equal to 0. So I'm going to come in here and write in my static friction. You can put a little s on it if you want to remind yourself later that that was static friction. So I'm looking at this thing, understanding, knowing that it's not speeding up or slowing down. In fact, it's not even moving down the slope. It's neither moving nor changing its motion. And so I know I have to have a balance of forces in both the x and y directions. However, if the acceleration is 0, which way do I make positive? Randall, say it louder. Whichever you want. Choose wisely. Before we had a rule of thumb, right? Whichever way you think the acceleration is happening, always make it positive, right? Well, with no acceleration, we're free to pick whatever direction we want. I've already implied the direction with the components that I've picked here, right? But do you see how 1, 2 of these forces are already perpendicular to each other, right? Don't pick a coordinate system where you've got to go find components of friction and normal force. Just don't do that to yourself. Is it possible to figure it out? Sure. It's just a lot harder. It's a lot messier mathematically, vectorally, psychologically, emotionally, all those different, right? Notice that if I go back to this tilted coordinate system, I'm automatically lining up with 2 of my actual forces. The third force that doesn't play nice, I already know how to deal with. I can find its components, right? We've done that a lot. So again, we will tilt our coordinate systems, maybe like that. Could I do positive down the hill? What do you want, up the hill or down the hill? Up the hill. Okay, fine. Feels better, feels more natural. So I only have one object, so mass 1. All right, x, y. What's the acceleration for x? 0. What's the acceleration for y? 0. Okay. This is going to get exciting. What do I have in the x direction? Friction and m1g sine theta. Friction, positive or negative? m1g sine theta? Negative. Okay. And then in the vertical direction? Normal minus m1g cosine. I don't know why I'm putting 1 on things. Apparently this is m1. Great. It's m1. Okay. And my normal force, I implied direction, but I better explicitly state that it is positive. Okay. Where's mu? Fun. Right? So I can go about this a bunch of different ways. I could solve fun for mu, which would be f over n, and then solve the 2 equations, one for f and one for n, and then just plug them in, right? That's one way to do it. I could insert the f right now into here, put the n into there, and then solve for mu. I really don't. I'll do it that way. Why not? I don't care. It's all math. Going to go that in there and this in there. So, and the normal force is equal to m1g cosine theta. So this is equal to mu m1g cosine theta. And then that one gets put over into here, killing math teachers. All right, so 0 equals mu m1g cosine theta minus m1g sine theta. Now I got to solve that for mu, right? Move some stuff around. Mu m1g cosine theta equals m1g sine theta. Be careful. Professional driver on closed course here. What did I just do? Notice how I moved the mu m1g cosine theta over. What should have happened? It should have become negative, right? But that was also negative. So it went away. That's fast math. The other way you can think about it is I moved the m1g sine theta over, and so it became positive, and then I just reversed, right, the order of writing the equation. Whichever way you want to think about it, or not think about it, you can just trust the math. I don't care. Okay, are there things that I can get rid of? Things that are the same on both sides. What does that mean? What does that mean that we can mathematically eliminate those things because they're the same on both sides, divide both sides by the mass? What does that mean physically? What are the implications? It doesn't matter if it's a Ford Bronco or a mouse or a tungsten cube or a banana. Like, it doesn't matter what the mass of this object is. What's the other thing that cancels? Little g. Not gravity itself, but the acceleration due to gravity. What does that mean? Where did we just solve this problem? Every planet. It doesn't matter what the gravitational acceleration is. So whatever result we get will work on the moon. It'll work on Mars. Won't work on Jupiter. No surface. Io, don't go there. Europa, don't go there either. All these worlds are yours except Europa. That was a quote from 2001: A Space Odyssey. 2010: A Space Odyssey. Titan's fun, okay? Titan, moon of Saturn, right? It doesn't matter where we go because the gravitational acceleration left, right? This is independent of object's mass, and it's independent of which planet we are on. We have solved all the problems. How did they know what coefficient they needed on the moon rover's tires to be able to go up hills? Solved it here on Earth. Didn't have to simulate lunar gravity. Okay. What am I done? What happens if I divide those sides by cosine? What's sine divided by cosine? What happens if you increase the angle of the slope of a hill? What happens to the coefficient of friction required in order to keep the static friction going? It gets higher and higher because the tangent of 0 is 0. But the tangent of 1 is, anybody remember? It's undefined. It's infinite. Okay? Tangent approaches infinity as it goes to 90 degrees, right? Which again makes sense because a hill that's 90 degrees is what? A cliff, right? And you'd need infinite sticking power for something to not slide, right? So, yeah, we now know what coefficient. Now again, that's the coefficient required theoretically. Practically, how do you get that coefficient of friction? Well, it depends on the materials that are being used, right? If you strap ice skates to a Ford Bronco and put it on an icy hill, right? The coefficient is going to be really small, isn't it? Which means that you can barely tilt that hill and whoop, we're going to overcome the required coefficient of friction, right? But if we put sticky rubber tires, right, on this car, then we can tilt this hill a lot because that coefficient will be really large. In fact, why is it that high-performance racing vehicles use sticky tires on the racetrack? They literally, like, the rubber comes off of them to melt into the surface of the track. They want grip, right? They want the ability, and we'll talk about this when we get to chapter 10, they want the ability to be able to corner, right? Oh, no, maybe we're going to talk about it right now, which is why I'm talking about it in my notes. They want the ability to corner, right, and stick. And the thing that causes a car to turn is the static friction between its tires and the road. The more coefficient you can build up because of the materials properties and what they're doing when they come into contact, the more force can be applied, right, to help that car turn at high speed. There is a discipline in motorsports where they don't want a lot of static friction. If anybody's ever seen the skill and art of drifting, where a car literally burning its tires, right, to do donuts and all kinds of neat tricks, right? That particular instance is one of kinetic friction. And what they're doing is they're kind of riding a regime of kinetic and static friction. And you can watch what happens when somebody's drifting and they lose it. And that sometimes they'll grip too much. Like they'll go from the kinetic friction where they have this nice, smooth, motion going, and all of a sudden the car will grip. Okay, and they'll kind of jerk around. Again, because static friction is so much bigger than the kinetic friction. If you haven't seen drifting, I would go to YouTube and just look up car drifting, and you'll see it's pretty incredible. All right, let's do that. Let's do a quiz, and then get into some circles. Whee! You know, a lot of things have happened since humans discovered fire, at least how to make it on our own. And I question a lot of them, and this is one of the things I question. Why do we do this to ourselves? Because it's fun. Oh, F equals mu n? No. PHUN? No. Why do we go we? Well, some of us throw up. But why do other people go, wow, this is so much fun? What's sensation? Like, what's the thing here? Ooh, weightlessness? Oh, like you feel like you're going to fall out of the contraption, maybe? Is there some element of danger?
Yeah, well, I'm strapped in with like 3 different belts.
And because it always comes, you know, half of those sounds don't have to happen. They deliberately like make noises and things to it's an experience, right? The experience used to be, I was in the grass and being hunted by tigers. And apparently we've gotten so safe that we now have to invent ways to scare ourselves. Right? It's not life and death, but it's fun. Whatever. It's all of those things and more. What we're going to concentrate on today is not the evolutionary history of our species, but the physics of everything that's going on in a loop-de-loop, in a turn. And again, your author decides to be kind of sprinkling and peppering some of these rotational things along the way, so it doesn't come as such a big slap in the face when we finally start doing circles for realsies. But we touched on circular motion before when we did chapter 4 with constant acceleration. Back then, we learned that there was an acceleration pointed towards the center of circular motion. It was called centripetal acceleration. And we had an equation that told us what the magnitude was. Do you remember what it was? You're not required to remember equations in this class. And of course, nobody remembers it because I didn't put it on the exam, right? That was the That was the magnitude, the number only, of the centripetal acceleration. What direction does this acceleration point? Towards the center, right? Okay. So in an effort to understand the physics of a vertical loop-de-loop, we are going to apply everything we've learned about Newton's laws, especially Newton's second law, to two different points on the circle. And to keep it simple, those points are going to be the top and bottom of the circle, where most of the whee factor is going on. So I'm going to draw a loop-de-loop. That didn't work. My tool gave up on me. There we go. Perfect circle every time. All right. We're going to do where the roller coaster, this could be a free body diagram of the roller coaster car. It could be a free body diagram of the person in the roller coaster car. It's going to be the same free body diagram. We can consider the person and the car all one object. We can think about just the person. It actually doesn't matter. Forces are the same no matter what. Okay, so we're going to do top and we're going to do bottom. We'll do top in green and we'll do bottom in blue. Let's do bottom first, okay? So at the bottom of the loop-de-loop, what things are pushing or pulling on the roller coaster car?
Gravity.
That's the force. The object would be the earth, right? And it points down or in. Anything else? Anything in contact with the roller coaster car? The track. Oh, okay. What force is that called? When two surfaces come into contact with each other. A normal force, right? And a normal force is perpendicular to the surface of contact. What direction is the perpendicular direction here? Up. Now, will that normal force change its direction as we go around the loop? Sure, right? If we're over here, what direction would it be? Yeah, ooh, towards the center, right? Constantly changing direction of normal force. Okay. Are there any other objects pushing or pulling on this roller coaster car? Friction. Okay, so there could be friction, right? It could be air friction. It could be rolling friction. We know there's static friction between the wheels of the car and the track. Let's ignore all of that. I can ignore it, well, because I say so and I'm the teacher, but also we're not going to change the speed at which this thing goes around the circle. So if it doesn't speed up or slow down as it goes around the loop-de-loop, what do we know about all the frictions and propulsions and everything that's going on? Like in the horizontal down here. If along this line, what do we know if the speed isn't changing, the v isn't changing? Acceleration is 0, which means that all those forces are balanced, right? Whatever they are, they add up to 0. Are they going to be doing anything for us? No. But there is an imbalance of forces, and I know it needs to be towards the center. How do I know it needs to be towards the center? It's moving in a circle, right? The acceleration we have is towards the center, and so therefore, I'm going to say my acceleration is up, in the case of being at the bottom of the circle, which means I'm going to make my positive direction be which way? Up. And now I can go ahead and write down Newton's second law. It's going to be ma equals, how many forces do I have? 2. Normal and the weight. Normal force, positive or negative?
Positive.
Mg? Negative. There we go. That's the bottom equation. All right? Do the same analysis for the top. Okay? Oh, okay, so force of gravity due to the earth. Which way is that pointing? Down? Just checking. Doesn't point up, right? Gravity never points up. So, points down. Which way does the normal force point?
Down.
Also down. Right? We're upside down now, aren't we? Perpendicular to the surface of contact means that the normal force is also pointing down. What direction is the acceleration? Towards the center. And what direction is towards the center when you're upside down at the top? Down. Everything's down. Such a downer of a problem. So what direction am I going to call positive? Down. And I just realized I wrote it in red. This is required. I have to fix all of it. Okay, there we go. I feel better now. All right, so what do we write down for the top equation? We've got ma equals. Normal force plus mg, right? There's only one sign difference, right, between these two equations. All right, what can we do here? We can do lots of things. Let's get the acceleration correct. So since we are going in a circle, we know that the acceleration is centripetal. So that's a centripetal acceleration. That's a centripetal acceleration, which means I can write this as mv squared over r. I just put in, right, substituted in my definition for centripetal acceleration. This would be normal minus mg. I'll do the same thing up here. Kind of doing these in tandem. And plus mg. And then, we can solve for speeds. We could solve for like radius of turn required. But let's concentrate first on the normal force. Because, believe it or not, it's this normal force that is giving the wee factor. You might think it's the speed that it is. You might think it's the radius. All that goes into it. But the normal force in this situation is what people are responding to when they talk about, hey man, that ride almost killed me. That and maybe throwing up a lot. So let's solve each of these for the normal force. Oops, that's red. So solving this for the normal force. Normal force is going to be equal to mv squared over r plus mg. And up here at the top, solving this for the normal force is going to be mv squared over r minus mg. Ooh, that's interesting. What's the difference between the top and the bottom when it comes to the normal force? Which one of these is bigger? The bottom. Why is the bottom bigger? Plus, right? Whatever mv squared over r is, and don't worry, I know you probably don't realize what it is, right? Okay? It's whatever that is plus gravity, right? And up there, it's whatever it is minus gravity. So where is a rider going to feel the most normal force? The bottom. And where are they going to feel the least? At the top. And why am I talking about normal force and the rider's experience? When you're sitting there in the chair right now, you are experiencing a normal force, right? The normal force of the chair is pushing up on you because you're pushing down on the chair, right? Why are you pushing down on the chair? Too many donuts this morning? Gravity, right, is pulling you down, right? So the interaction between you and the earth, there's a force, right? But the chair gets in the way, right? There's a surface of contact. And there's a separate pair of action-reaction forces where your rear end and the chair are involved. You think of your weight as not the force of gravity pulling on you. Well, maybe that's the way you think of it. But the thing you feel, the force that's applied on you, is normal forces. When you stand on a scale at the doctor's office or in the bathroom or something like that, right? Okay? Does the scale know your weight? No. What's the only thing the scale knows? How much you are pushing on it and how much it is pushing on you. Right? We think of our weight as normal forces. In fact, if somebody jumps into a swimming pool, they will often say that they feel like their weight is gone. They're just floating. Right? Meaning that they feel like there's no normal force, right? There's no surface of contact required to float in a pool except for the surface of contact, which is the water, right? Okay. What we're talking about here is a phenomenon called apparent weight. So let's do a thought experiment here, and then we'll get back to the roller coaster. We go into this building, and we get into the fancy new elevators, and we're on the bottom floor. We push the button for the third floor, right? Okay, doors close. What do you experience? All of a sudden, I got heavier. Right? You feel heavier as that elevator begins to go. There's going to be a bunch of you riding the elevator after this class, isn't there? That feeling of like, ugh, right? Now, did the earth suddenly begin pulling on you more? No. But I bet you if you ask people what happens to you when you get in the elevator, they say, I weigh more. Did that Twinkie affect you that fast? Did Earth's gravity somehow suddenly change inside of the... No, none of those things happened. What happened? In order to accelerate you upward, to change your motion, to get you to the top floor, what did the elevator have to do? Push up on you via the normal force, right? And so your normal force had to get bigger than the gravity pulling you down to get you to accelerate upwards.
So, if you were to bring a scale with you to the elevator,
Yeah.
it would change.
Yeah. My former school, we didn't have regular labs, we had walk-in labs, and students would check out scales from the physics lab equipment room, and then they would go on campus and ride elevators all over campus. People were so pissed, right? Because the physics students were jamming up all the elevators, right? And we'd have them put it there, we'd have them record their weight, right? As the elevator began to accelerate. And you can see it on the scale. The scale says more. Why does the scale say more? It's pushing you upwards, and the only force it has is normal force, right? It has to overcome your weight, the gravity pulling on you, to get you to accelerate upwards. Okay, now we're arriving at the 3rd floor. And now all of a sudden, instead of feeling heavier, what do you feel? Whoa, my weight loss is working. Again, gravity didn't change. Your mass didn't change. What changed? The normal force, right? We constantly think of the normal force acting on us as our weight, and it's not. You have weight when you've jumped out of an airplane, right? You have weight wherever you go as long as you're being influenced by a gravitational body. Apparent weight, the weight that a scale gives, the weight that everybody would swear is their weight, right, is really the normal force that's acting on an object. So in an elevator, you will, quote unquote, feel heavier as it begins to go. You will feel lighter as it comes to a stop. Okay, again, because the acceleration has to be down now, right? You were moving upwards, but now you need to come to a stop. So acceleration's down, so normal force has to be less, and you'll say, oh, I got lighter all of a sudden, right? In between, when your speed is constant, what do you feel? Pun intended, you feel normal, right? So let's bring that thought experiment into this reality, right, of riding a roller coaster. At the bottom, a person will experience a normal force that is the result of their inertia, right? They want to keep going in a straight line, but the roller coaster's not letting them, okay? So they'll feel their inertia, plus the weight of gravity, true gravity, acting on them. In other words, the normal force will be big down here. They will report that they feel what? Heavier. Pushed into the seat. Crushed. Oh, the G's, man. Right? But at the top of the loop-de-loop, what do they experience? Inertia minus gravity. The difference between their inertia and gravity, meaning that the normal force is less. Meaning that now they feel like what? Falling. Right? And all of this takes place in less than a second or two, right? At the speed that that roller coaster is going around, they'll go from to as they go around that loop-de-loop, with all the things in between. In other words, the wee factor. Is there a speed that we can find where the person will be truly weightless? Is anybody ever truly weightless? No, because strictly speaking, weight is what? The force of gravity acting on you. In order for you to be weightless, what has to go away? The earth. Okay, that's not happening, right? But in the context of what everybody thinks of as their weight, right? This normal force, this apparent weight, is there a situation where the apparent weight, this normal force, could go to zero? Sure, let's figure out what that is. So, if normal force goes to zero, right, then a rider is going to say, I am now weightless, right? I'm no longer in contact with the chair. Then that means this has to be the case, right? And so I'm going to rearrange some things. mv squared over r equals mg. I did my little trick where I moved it over and there was a double negative, so I got rid of it. What's the same on both sides? I didn't write it clearly. mv squared. What's the same on both sides? The mass. So does it matter if we have a rider who is small mass versus a rider that's big mass? No, this works for all riders. Why do they say you must be this tall to ride this roller coaster? Safety equipment, right? The thing that keeps you in the seat in the case of a malfunction. So what have I got here? I've got v squared equals r times g, or v equals the square root of rg. That right there, that's the speed that this roller coaster needs in order for a rider to no longer be supported by the seat that they're sitting in. If the roller coaster goes at that speed, the square root of the radius times local gravitational acceleration, then they will feel weightless, meaning their apparent weight has gone to zero. It also is the exact same speed that the car would leave the track. So how do you make it so that the rider feels weightless, but the car doesn't come off the track? You wrap wheels around the track. So on a roller coaster, here's a track. It's a bar, right? And they have wheels on both the top and the bottom of the roller coaster car, right? So if the car's upside down, there's a pair of wheels that's holding it onto the track up there, right? So they figured that out, right? But if they didn't have the second set of wheels, right? And there was nothing holding it onto the track, that could be a problem if you're approaching this speed, right? Okay. Also note that this only works where? At the top, at the very top of the loop-de-loop. Nowhere else in the loop-de-loop does this apply because the vectors, there's different components and all that kind of stuff. You might notice how in the picture example that I provided, this roller coaster is teardrop shaped in its cross section, right? It's not a perfect circle like I drew in my example, doing the math. Any guesses or knowledge as to why they would not do a perfect circle in a loop-de-loop? I don't know if it's more, it's a good question. I don't know if it's more or less energy. We could do that analysis. So what's happening here, notice how the radius, the radius of the curvature of this track is changing constantly. Okay, it's got like a really big radius down here, and then it kind of tightens up and then comes back out, right? Okay. With that teardrop shape, engineers discovered that they could effectively increase this window where the rider feels weightless, right? So they did make perfectly circular roller coasters, okay? And they had a certain amount of fun. But if you really wanted somebody to kind of feel like they were falling out of their chair, it needed to be more than like an instant, right? It needed to be few milliseconds or tens of milliseconds of time for human awareness to realize that something, oh my gosh, I'm going to die. Oh, I'm not going to die, right? Okay? To pull that kind of biology and psychological reaction off. So they extended the window, right, where that weightlessness would occur. They also noticed that riders complained on circular roller coasters of coming in and out of the circle. Because at that bottom point, that's where you're the most pushed down, right? But there was then only that one point where you felt light, and then another point where you felt crushed down. So by extending out the curve in and out, they're making a gentler entry and a gentler exit, right? But still getting that, whoa, I'm going to fall out and I'm going to die type of experience. So there you go. The physics of roller coasters ruined forever for you the next time that you happen to go to one. I don't think it's ruined. I think roller coasters are more fun now that I know how they work. Let's see, chapter 5 is due this Saturday, right? We're in chapter 6, so we're ahead in lecture, so you should be just fine for chapter 5. If you need me tomorrow, tell a tutor, they'll come find me. If I don't see you in Grasp, have a great weekend.